Lesson 6.5, operations with radical functions. So radicals, we're talking about roots, maybe square roots, cube roots. So I'll do a quick example with you guys, what we're basically talking about. Suppose you want to take the square root of 18. You want to simplify that. How can I write it simplify? Well, if I make a factor tree with 18, what does 18 break down to? How about 2 times 9? And 9 breaks down to 3 times 3. Right, so 2 times 3, right? I can think of it like that. So what's the square root of 2 times 3 times 3? That's what my factor tree said. Right? Right. Oh, and hey, look, I have a pair of threes. Well, if I'm taking the square root of a pair of threes, that could just come out as a solid 3. So it's 3 times the square root of 2. Okay? So what I'm saying is that this and this are the same thing. And let me show you guys that with the calculator. If I do square root of 18, 4.24, I'll jot that down. 4.24, now it's irrational, so non-repeating decimal. Let's cut it off at some point. 3 times the root 2. Let's see if I get exactly the same thing. And oh, yep, sure is. It's exactly the same thing. Okay, so just like that. Oh, I bet if I had a triplet of numbers, I could do a cube root like that too. I'm sure that'll show up pretty soon. Okay? And a lot of these puzzles in this lesson are a lot like that. Near the end, the last example they gave, I'll flip to it real fast just to show you guys. A little more complicated is it use conjugates to rationalize the denominator. So that one's a little more exciting. There's some pretty fun word puzzles in here. We got a distance. We got a music example down here, like tuning musical instruments. Right. So yeah, let's go through these book puzzles. Start with these examples right here. And so example one. Uh, well, I'm going to do B first, and then I'll cut back to A because B is a square root, A is a cube root. So why not? Okay. Right, so 1B, example 1B, we got the square root, we got 75, we got x to the 12, and y to the 7. Okay, just like that. Okay. Now 75, what does that break down to? Well, I know 3/4 is 75 cents, so that could be 3 times 25. And 25 breaks down to 5 times 5. Okay, so I think 3 times 5 times 5, that could be this. Okay. So let me write that. So we got square root. In place of 75, I'll do 3 times 5 times 5. Okay. And play, oh, x to the 12. Now I could write out 12 x's. Hmm, let's see. Okay, so could that be the same thing as like x squared, x squared, x squared? There's 2, 4, 6 x's, 8, 10, 12. Okay, yeah. Or is that okay? You guys know if you're multiplying a string of numbers together like this, if you add they all have a common base, in this case x, you can add the powers. And so these twos all add up to 12 in this case. And y to the 7, maybe something thing. Uh, I could write this out as 7y's. Here, I'll go ahead and expand this one out just to give you guys a little bit different visual on this. 4y's, 5, 6, 7y's. That's y to the 7. Okay. So let's see. Can I pull out any pairs of numbers? Yeah, a bunch. I have a pair of fives here, so I'll pull out as just a solid 5. I have one, two, three, four, five, 6 pairs of x's. Remember, there's 12 x's altogether multiplied. So I can pull that out as x to the power of 6, right? Because the square root of x squared is x. And that happens 6 times. Look at that. And then now the y's. I have a pair of y's there. There's 1 pair, 2 pairs, 3 pairs. And then, well, I ran out of pairs. So I can pull out 3y's. Okay, so that's y to the power of 3, I should say. Okay? Now, I do have leftovers. I'm going to write times the square root of. And I still have this 3 right here that I could never do anything with. Now all these x's were taken care of. 3, 4, 5, 6, after there. But I still have this last y on the end. I couldn't really take that out either. I can't simplify. So I think this right here is the simplified answer. Okay. Let me show you guys that that's true with a numerical example. Right, watch this cool trick. X and Y. Now that can be kind of abstract, right? But could you really make up anything you wanted to for X and Y? I'll say, for example, I'll just make up something on the fly here. What if x was equal to, how about 5 and y is equal to, how about pi? This is completely crazy. Right? I just made that up. Right? But what I'm trying to show you guys is that whether I plug it into the original expression or my simplified expression, I will get the exact same decimal answer. Let's do square root. Right, square root here. I got 75 x to the 12. Well, I'm going to say 5 to the 12 because I decided x is 5 now. Right? And then I also got y is pi, so that's pi to the power of 7. Now this is all underneath the square root. So this comes out to 7, is that 7,436,614 around the Okay, so it's 7.4 million something. Okay. All right. How about this expression right here? So 5 times, and then, okay, well, x I also decided was pi, so x was 5. So 5 to the power of 6 in this case. And then y to the 3. Well, y is pi, so that's pi to the power of 3 now. That's all multiplied. And then times the square root of, and then 3y. So that'd be 3 pi in this case. And close parenthesis. And do I get the exact same number? If I do, then this whole process works and we're good to go. Oh yeah, cha-ching! It's exactly the same thing. Yeah, this is all working. So how about that cube root that I skipped? I'm rounding back to now. I got a cube root example, 1a. I got a cube root, and a lot of times like, I'll write this as a power of 1/3. You guys know that? Okay. Got negative 27, a to the 6, b to the 14. Well, square roots, we're looking for pairs of numbers multiplied together we could pull out. I bet cube root, we're looking for like triplets of numbers. Like, what does 27 break down to? You could say 3 times 9, or I'll just cut straight to it. 3 times 3 times 3. Okay, isn't that 27? Okay. So I could write it that way. Let's do cube root. Just for funsies, I'll rewrite this cube root as a 1/3 power, just to remind you guys you can do that. So 3 times 3 times 3, a to the 6. Hey, isn't that like a to the power of 3, a to the power of 3? That brings you up to 6 a's multiplied. And then b to the 14. Well, there's 3 b's, 6 b's, 9 b's, 12 b's. Ooh, but we're running out. I just need 2 more b's to bring it up to 14. All right. I could throw this all under a cube root, or I could take it all to the power of 1/3, however you like. It's the same idea, right? Okay. And now that I have that triplet of threes, I can pull out as a 3. Actually, while I'm at it, I may as well pull out the negative, because you guys know a cube root of a negative. You just pull the negative out front. -1 times -1 times -1 is -1. Okay. I have a triplet of a's here, so pull that out as an a. Ooh, I have another triplet of a's here. So you pull out another a, multiply that makes a squared. Okay. And then there's 1b I can pull out. 2, 3, 4. So I'll say b to the 4. And then I'll say multiply by, here, I'll go and switch my notation back. Okay. Because I still have some stuff left over. Actually, not much, just this b squared. This b squared, well, can't really simplify that anymore. Right, so that's simplified. It's the same thing. Yeah, but we are good. We're good. Now, if you weren't 100% sure on that, remember, you could always make up random numbers for x and y, like I did for the last example. I said, oh, let's call it 5 and pi. Oh, right. And I plugged it in. For first expression, simplified expression, it came out to the exact same value. The same thing will happen here to here. Right? No, I'm not going to do this video just to save a little time, but if you want to, you totally could. And I'm guaranteeing it's going to work. Right? So move on here. Let's do example 2. Quotient property. Well, this is basically the same thing. It's just a fraction, but there's nothing super much new crazy about this. Let's do 2a here. Okay. Well, okay. We're doing another cube root, I guess. Got a cube root, and now it's a giant fraction. What we got on top is a 24a to the 6, and the denominator is 125. Okay. Well, what do these values break down to? 24. I know that could be 8 times 3, right? 8 times 3. Oh, and 8 is 2 times 2 times 2. Okay, hey, there's a triplet of 2s. Okay, well, I know that's eventually going to be pulled out. How about this 125? Well, I know 5 times 5 is 25, and 5 times that is 125. So this is a triplet of 5s, isn't it? 5, 5, 5. Multiply that, gives you 125. Okay. So here, I'll rewrite this. I got a cube root. I got a fraction under there. 24 is the same thing as a triplet of 2s. I still got a 3 in the mix. Okay, so that's also part of that original 24. In the denominator, I got a triplet of 5s, so I'll think of it that way. And then a to the 6. Hey, isn't that like a cubed? Isn't that what a to the 6 is? You could think of it that way, like that. Notice I extended my fraction bar a little bit. If you ever did, or my root bar, if you ever don't make your radical bar long enough, you're like, you're writing more stuff, go ahead and extend it like I just did. Otherwise, you'd be communicating to whoever is reading your work that maybe these numbers are not part of the radical when they definitely are. Right? If I didn't extend that would be different than that. All right. So what can I do? I can pull out a 2 on top. I can pull out a 5 in the bottom. Nice, I got that. And I can also pull out an a there and another a there. Now those are multiplied, so a times a, that gives me a squared. Okay? And multiply it by, and then cube root. And I still have this 3 there, so I've got cube root of 3. And that's it. Right? I pulled this out, I pulled this out, I pulled both these guys out, and this guy's left. Yeah, so check all my boxes. Okay. Right? And of course, you guys know that this cube root of 3 could be part of the numerator, like if you just wanted to show this all in one giant fraction. Okay, so that would also be true. All right. How about part B? It's 2B. Hey, now we got a fourth root. Ooh, a fourth root. Well, not maybe I'm just looking for groups of four of something. Let's see, we got an 80. We got a y to the 14. Ooh, 256 and z to the 4. Okay. So, see, what does 80 break down to? Factor tree. See, that could be 8 times 10, right? I don't know, that's one way to do it. And then 8 is 2 times 2 times 2, and 10 is 2 times 5. Oh, yeah, look, we do have four twos right there. Yeah, them together now. How about 256? Ah, well, I know it's divisible by 2. Let's see. If I do divide by 16. Oh, you know what? You know what? I know those two. Isn't it 16 times 16? Right? And 16, isn't that 2 by 2 by 2 by 2? Right? Yeah, it sure is. Okay. Okay, so it's a little different way of thinking about it, but yeah, a lot of times math there. All right, so let's go back to the premise here. I got a fourth root. Ooh, a fourth root. In place of 80, I'll do 2 to the 4, and I still have a 5 in the mix. So drop that guy down. In the denominator, I have 16 times 16. No, 16 is 2 to the 4. 16 is 2, 4, 8, 16. Right? I just showed you guys that. So I'll think of it that way. 2 to the 4, and then another 2 to the 4. Oh, you know what? I wasn't expecting this, but these are going to cancel out, aren't they? Before I forget, let me get my y's and my z's in here. So y to the 14. Well, that's y to the 4. There's one group, because I'm looking for groups of 4. That's why I did. There's 4 y's. That brings me up to 8 y's. It brings me up to 12 y's, and I'll have 2 y's left over. Extend my radical, extend my fraction. And from z to the 4, yeah, well, that's exactly like I wanted there. Okay, so now this is ready to take on some roots. Okay, let's go ahead and cancel that. Well, the 5's kind of stuck there, so I'll leave it there. Okay. In the numerator, I have a y I can pull out here, because the fourth root of y to the 4, that'd be y. A y here, a y here. Okay. And I think that's all I can take out of the numerator. So I got 3 y's I just took out. 1, 2, 3. In the denominator, there's a 4 because the fourth root of 2 to the 4 is 2. And the fourth root of z to the 4 is z. So I take out 2z. All right, multiply by. And I still have a fourth root, or power 1 over 4 if you like. What have I got left? Okay, I got this 5. And I've got this y squared, which, well, it's only 2 y's, not 4, so still stuck in there. Y squared. Yeah. I guess if you really wanted to poke around with it, here. This is just really a side thought. I don't know. If you plug this into Alex, it might give you full credit. But if it didn't, here's one of my guesses why it might not. Y squared, and then the fourth root of that, guys, isn't that really like 2 over 4 as a power? And 2 over 4 isn't that reduced to 1/2? Which you could also call the square root of y, not the fourth root, but the square root. And so this is a little thing I see, but yeah, I think that's probably fine. Yes, like that. All right, moving on. Example 3. Oh, add and subtract radicals. Add and subtract time. Well, if you're adding or subtracting something, you have to have like some common factor or something. Like x plus y doesn't really simplify, but if you had x plus 2x, that could be 3x. And so let's see if you had these 3 terms here, 3 terms. If they had something in common, then maybe you could add those things in common. Like 1 apple plus 2 apples is 3 apples. Okay, let's try that. So we got 6, that's example 3, times the square root of 45x plus the square root of 12 minus 3 square root of 20x. What are we supposed to do here? Interesting, that middle one doesn't actually have an x term. So I think the square root of 12 is just going to end up by itself one way or another. But how about this 45 and this 20? Here, let's do a factor tree right here for 45. I know that's 9 times 5. And I know 9 breaks down to 3 times 3. So 3 times 3 times 5, that's 45. 12 breaks down into 4 times 3, and 4 is 2 times 2. So 2 times 2 times 3. Okay. And then how about 20? Well, 20 breaks down to 4 times 5, and 4 is 2 times 2. Right. Okay. Yeah, we'll be able to simplify this. Okay. So what we got here? We got 6. Okay. Now 45, remember, is 3 times 3 times 5, so I can take out a 3 because I got a pair of 3s, so I got a 3. And, well, nothing else. So what's left inside is I got this 5 stuck in here, and also this x. I got that. Okay. I'll say plus for that plus right there. Square root of 12, that's square root of 2, 2, 3, so I can take out a single 2, which comes from right there. And I still got the square root of 3. Okay. And then over here I'll do minus. And then I got this 3. I can take out this pair of 2s as a single 2. And then so I can take out, so that times the square root of. And I still got this 5 here. And I still got this x. Okay. Aha! Aha! Look at this. Look at this. These two outside terms, first term, this last term, both have a root 5x. That means I can eventually combine these down the line. Now this middle guy is, again, kind of his own thing, but let's simplify this. This right here, this is 18 times 3, 5x. That's 6 times 3, 18. Okay. This is plus 2 root 3. This is my 3 times 2 is 6. And then root 5x. Okay. Now root 5x and root 5x, that's like, here I have 18 apples here, and I'm subtracting 6 apples over here. Well, 18 apples minus 6 apples would then be 12 apples. Okay. But instead of apples, it's root 5x. Okay. So I got 12 times the root 5x, and then plus 2 root 3. That should be it. Yeah. Okay. Again, if you wanted to check this with a calculator, the way you could do it is you could make up a number for x, like pi, for example. You could plug that value for x into the original statement, and you can plug that same value in for x to the final statement, and these two are going to be exactly equivalent numerically. Then you would know. You got it right. Multiplying radicals. Example 4. So got 4. Oh, they're going fifth roots. Okay, so that's kind of exciting. Fifth roots. Got a negative. Got a 10. X squared y to the 6. Okay. All right, so then the radical closes. Right now we're multiplying that all by. We got a 3. Got another fifth root of 16. X to the 4, y to the 4. Okay. Now, since I have a fifth root and a fifth root, I could just combine those all under like one giant umbrella. You could do that. Actually, everything's multiplied. You guys notice how nothing is added or subtracted? Everything's just straight multiplied. Right? So multiplication, they could be commutative, so you could multiply in any order. I'm going to bring this 4 and this 3 together. I'm going to make that 12. Okay, they're a little math. Okay, where does 12 come from? That 4 comes out 3. Good, that's all. Okay. Oh, you know what? While I'm at it, how about I take this negative out? I'll just bring up a negative because it is an odd root of a negative, which means I could just take it out. Because if you multiply -1 times itself 5 times, it's still -1, right? All right. What else we got? So I'll say multiplied by, I got a fifth root of everything else. I haven't touched it. I got let's see, a 10 and a 16. If I'm thinking ahead a little bit, guys, isn't 10 2 times 5? So I'll go ahead and say 2 times 5. I got an, here, I'll just bring all the numbers together. 16 is 2, 4, 8, 16. I think it's 2 to the 4. So that's times, I'll spell out 2, 2, 2, 2. Right. So we're getting all this stuff. So this 10 just became this 2 and 5. This 16 just became the string of 2's, because 2 by 2 by 2 by 2 is 16. Okay. Here, I'll bring the x's together. I have 2 x's here and 4 x's here. Again, all multiplied. That's like x to the 6. And then 6y is 4y, that's 10 y's. Y to the 10. Okay, that's all under that fifth root. That fifth root. Okay. Now, here, I'll throw in a middle step here. I don't know if this is 100% necessary, but if you want to see a little bit different perspective, then notice I have 5 2's. So I could write that as, I still got 5, right? As 2 to the 5th. So I got that. X to the 6th, isn't that the same thing as x to the 5th times x to the 1? That's x to the 6th. And then y to the 10, isn't that y to the 5th times y to the 5th? Yeah, just a little middle stuff I threw in just so you can see it a little bit differently. Okay? And I say, hey, the fifth root of y to the 5th is y. Well, the same thing here. Fifth root of, okay, then that. I can, everything I just circled, I can pull that out one way or another. And I still got this -12. I'm going to pull out 2 to the 5th. The fifth root of that is just a plain 2 now. Yeah. And then x to the fifth root is x. And then y to the fifth root is y, but there's another y, so that gives me y squared. Then multiply by, then I have the fifth root of everything left over, which is this 5 and also this x. That's what I got left. Okay? And the last thing you can do to clean this up is just combine these constants, 12 times 2. Right? So we got negative 24 xy squared, all multiplied by the fifth root of 5x. Yeah. Same thing. Oh yeah, same thing. All good? Yeah. Four. Ah, okay. Good. We got a word puzzle. Example 5. A sports pennant is shown, so a triangle shape. I got one behind me. The Vera hooks. Find the area in square inches. Find the area. I mean, that is a triangle. Okay. They told you how tall it is here and how wide it is here. I know that the area of a triangle is 1/2 base height. We say base height over 2. Yeah, every other thing. So, hey, they gave us the base and the height, but we could just plug it in, see what happens. Okay, so area is, yeah. So let's see where this goes and what connection does this have with this lesson. The base, here, maybe I'll call this the base. 7 times the root 8 plus 6 times the root. I wonder if these numbers are real or accurate or what. You know. And then the height, I got 3 times the root 8 plus 4. I wonder if there's some reason for these back-looking numbers or it's just an academic example. But if we want to see, combine all this, how do you simplify it? See, I mean, this could totally be the answer right here, right? But maybe there's a way to simplify it. So let's go FOIL, F-O-I-L, because you got two terms, everything multiplied. I could go first, outside, inside, last, and then 1/2 after all that. So see where this goes. I got 1/2 times, put some brackets. First, 7 times 3 is 21 times root 8. Hey, that becomes just plain 8, right? Because that came from square root of 8 times the square root of 8 is 8. That's why I wrote that. Okay. Outside. So 7 times 4 is 28, and that's times this root 8. Plus inside, I got 6 times 3 is 18. Well, what do I want to do with this? There's probably different ways to think about this. I'll go ahead and write it this way. Square root 3, square root 8. Okay. And then last, I got 6 times 4 is 24. And then it's like I thought square root 3. Okay. So I think this is sending us in the right direction. Okay. Something else I see here too is the square root of 8. Here, maybe I'll write this in the corner. Square root of 8 is the square root of 2 by 2 by 2, which is the same thing as 2 times the root 2. Okay. A little thought cloud here. And maybe I'll insert that right here, see what happens. So the area is, okay, so I got 1/2, okay, in my brackets. Now what is 21 times 8? Something big, 168. All right, so that comes right there. Okay. Then I know this bit right here is 28 times 2 root 2. So that's 56 root 2. Okay. If you want to check out here, I'll show you guys. 28 root 8 is like 79 point something, 79 point something. Watch this. 56 root 2. It's the same thing, 79 point something. Like I said, we're good. Okay, and then I could do the same thing right here. Yeah. So 18 times 2 is 36. And then, well, I got the root 3 and a root 2, and that doesn't really simplify. So, yeah, it's all right. Plus 24 root 3. So I'm really tempted to say, I'm seeing these root 2s and these root 3s floating around. Like, could I somehow combine these? And I really want to, but I don't think it does. Yeah, actually, going to over their answer, it looks like they're adding different terms together. So, root 6, root 2. Yeah, they got 4 terms in their answer, and I have 1, 2, 3, 4 terms basically. Once I distribute the 1/2, which we can do right now. So area is what's half of gives us 1/2 distributes boink, 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 boink into each of those 4 terms. So what's 168 over 2 is 84 plus 56 on 2 is 28 root 2 plus 36 over 2 is 18. Now I may as well just combine this 3 and 2, make the root 6, and then half of 24 is 12. 3. Okay, so I just distributed that half, right? So I think this could be a pretty good answer right here. Yeah. Now this would be in square inches. Yeah, square inches. So inches squared, square inches. There you go. Pretty good. Ooh, we got two examples left. Rationalize the denominator. And the last one we're gonna head to is the same idea, but with conjugate pairs. Okay, so, and we'll jump into the book puzzles. Example 6. Simplify this. All right. So we got a cube root for this example. We got inside the root is a fraction. We got 250 a to the 6 all divided by 7a. Okay. All right, so how can we simplify that? A lot of times, I never figure out why. I don't know. Mathematicians don't like there to be radicals showing up in the denominator for some reason. Okay, so there's ways to rewrite it, and that's exactly what this example is about. So let's see what this would come out to first. Okay. What is 250 on a factor tree? Well, that could be 25 times 10, couldn't it? 25 and 10. And 25 breaks down to 5 times 5. 10 breaks down into 5 times 2. Oh, look, I have a triplet of 5s, and we're taking a cube root. Okay, so that could be handy. Okay, I'll go to rewrite this. I got a cube root. 250 is the same thing as 555, and there's a 2 in the mix. A to the 6, that's like a to the 3, a to the 3, all divided by, we got 7a. So we got, okay, now what? Okay. Well, I got this triplet of 5s, triplet of a's, and another triplet of a's. So I can pull all that out as 5, and then a and a gives me a squared. And that's all multiplied by the cube root of, and inside I have a 2 divided by 7a. Okay. Now, for me, I'd say, okay, that could probably be simplified. That's good. Right? But again, mathematicians, for some reason, don't like radicals in the denominator. So we need to bring this up to a point where we're not having a radical in the denominator. That's how we did. Well, how does this? I'll put this in pinking so maybe it stands out a bit. What if I extend this radical, extend this fraction bar? Okay. And if only this a was a to the power 3, I could pull that out also, couldn't I? And I need two more a's to do that. If it was a times a squared, that would be fantastic. And I can do that as long as I balance it out in the numerator with another a squared. Yeah, because if you multiply a squared over a squared, that's like multiplying by 1. It doesn't really change anything. It just manipulates it so that there's no more radical in the denominator, or there's not about to be. And it's the same thing with the 7. I can say times, how about 7 squared, and then another 7 squared here to balance it out. It could be like that, right? Same thing. Okay, watch where this goes. So I got 5, got an a squared. Okay. And now, look, I have a triplet of a's down here, a. So I can pull that out as a solid single a. Okay. And then 7, 7, and 7, that's 7 to the 3. I can pull that out as a single 7, like that. And then multiplied by, and then I got a cube root. Now, everything else is just in the numerator. In fact, if you want to just extend this fraction bar, this is all numerator from here on out. I got, let's see, 7 squared is 49 times 2 is like 98. And then a squared, right? And none of that has any kind of cube root factor I can pull out. So, wait, there's one more thing I can do. A squared divided by a does not just leave you with a. So here, all right, in its final form, I have 5a times the cube root of 98a squared. That's all divided by 7. Feel like think of it that way. Okay. Let me give you guys an example, numerical example. Let's say, for example, what if a was equal to pi? Then this whole expression is equal to, let's say, if a is pi. I'll go back to the beginning. What is 250 times pi to the 6 divided by 7 pi? And that's all raised to the 1/3 power. I'm getting 22.19, I'll call it 22.2 around to pretty close. Okay. Would that be the same thing if I plug in a to this boxed in expression? It should be 5 pi, and then in parentheses, 98 pi squared, close parentheses, power third, and then that's all divided by 7. Yeah, it's exactly the same thing. Yeah, check. Bing. Very good. Rationalizing denominator. There you go. Okay, so that'll show up later in the book puzzles. And we'll do one more example, which is also rationalizing the denominator, but it's with conjugate pair. You guys remember conjugate pairs? You guys saw those back in the complex number days. So here, we'll try it out, see what happens. Example 7. We got 4x divided by 2 times the root 7, and then minus 5. Now, how this is different from the last one is, see, in the last one, we weren't adding or subtracting in the denominator, but here we are. Okay? But this does have the same problem as the previous one, which is that there's a radical in the denominator. Say, okay, well, what's wrong with this? How could you want to simplify this? Well, how can we get the radical out of the denominator is the question. And the way to do that is to multiply by a conjugate pair. Here, so I'll write the conjugate in thinking, so sort of a creative week here. Is, well, what if you had 2 root 7 plus 5? You guys remember that's a conjugate pair? You guys remember conjugate pairs? Okay. And so instead of minus, you just throw in a plus, and we're eventually going to FOIL this out, but that'll be the next step. But before I do that, I have to restore balance by putting this also in the numerator, 2 root 7 plus 5. Okay. Remember, the theory of why this works is that right there that you guys are looking at, that's effectively equal to 1. So if you multiply by 1, it doesn't really change anything other than getting the radical out of the denominator. Let's do some FOIL. FOIL. First, outside, inside, last. And watch all these square roots disappear. That's kind of the purpose of the conjugate pair, right? So I got a, on top, I still got this 4x. I'll eventually multiply those 2 root 7 plus 5. I guess I could distribute that, couldn't I? I'll say that for next step. And the denominator, 2 root 7, 2 root 7. Well, 2 by 2 is 4. Root 7 is 7. So we got 4 times 7. I guess that'll become a 28. That's about to become 28. Let me show you guys that that's true. If I do open parenthesis 2 root 7, and then I square that, it should give me 28. Yeah, it's totally 28. Yeah. All right, so then now the outside and inside cancel. Look at that. 2 root 7 times 5, 2 root 7 times negative 5, outside and inside cancel. Right, and then negative 5 by 5, I got a minus 25 here because 5 by 5. Okay, so yeah, all the square roots are out of the denominator now. They're gone. Right, that's what this conjugate pair was about, the denominator. So still got some cleanup work I could do. I can distribute this 4x into each of these two terms. And then I can treat this as 28 and subtract 25. So I'll do that. So that's 4x times 2, that could be 8x. And then, I still got to root 7. I guess we could put it there, why not? All right, and then plus 4 times 5 is 20. That'd be x. Okay, and then this is all divided by 28 minus 25 is 3. There you go. That's it. Now let's jump into the book puzzles. Book puzzles. All right, so I got some pre-highlighted. All right, so number 7. What's square root of 25 over 36? And there's an r squared t that's still underneath the radical. Now, they wrote it to the side of the fraction. You could totally just bump that in the numerator of the fraction. It's the same thing. Okay? Well, 25, isn't that 5 times 5? And 36, isn't that 6 times 6? So I can pull this out here. That's like 5 over 6. And then times square root. You know what? Oh, I can pull out an r. Ooh, it's r squared square root. That's just r. Okay. And I still got square root of t. Boom. Done. Next one. Oh, well, next one is a little more exciting. Let's get some more paper. We've got a fifth root. Fifth root of, okay, so looking for quintuples of things. 3,072. H to the power of 8 divided by 243 f to the power of 5. Okay. Let's do factor tree. 3,072. What does that break down to? Well, I have a suspicion. I do see it's even. We are taking a fifth root. So I have a suspicion that you could divide out 2 to the 5. What is 2 to the 5? 2 to the 5 is 32. Let's see if I can take a 32 out of this. What's 30? 32 divided by 32. It's 96. 96. Is that also divisible by 32? It sure is. That's 32 times 3. Huh, interesting. Right. And then how about 243? 243. Let's see. Okay. Yeah, I can take a bunch of threes out of it. Is that 3 to the 5? Is that what that is? That's exactly what that is. It's 3, 3, 3, 3, 3, all multiplied. Okay. All right. So there we go. Okay. 32, by the way, is 2 to the 5. Maybe I should have written it that way. Go a little thought cloud. So 2 to the 5 here, 2 to the 5 here. All right. So bring us back. So I got the fifth root of. Now 3,072, that just came out to 2 to the 5 times another 2 to the 5. And I have this 3 left over, so times 3. Now h to the 8, isn't that like h to the 5 times h to the 3? And I just broke it down like that because I can take out h to the 5 to 3. Okay. And then down here, 243 is really 3 to the 5. And then I have f to the 5. Okay. All right, what can I take out? Let's do 2 to the 5th, another 2 to the 5th, a 3 to the 5th, an h to the 5th, and a 5 to the 5th, and f to the 5th. Pull all that out. So that'll come out as a 2, another 2, divided by the 3 down here. Okay, there's an h on top, there's an f on bottom. I just pulled all that out of the radical. Okay, but there's stuff left over. So times the cube root of, and here we have, or sorry, not cube, the fifth root. Oops, there you go. Fifth root. I still have this 3, and I still have h to the 3, and those are just kind of stuck there. All right. Yeah, I think that's about all I can do. Maybe put those twos together. 4h on 3f times the fifth root, or to 1 over 5 power, if you like. 3h to the 3. I said, that's probably what they're looking for. It's not bad. All right, number 11, simplify. Oh, so we're adding the root 2 plus the root 8 plus root 50. Here. Well, at first it looks like apples and oranges and bananas, right? But I think I can simplify these and get these all in terms of the root 2. And then it'll be apples, apples, and apples. Let's do that. Because I know 8 is 2 times 2 times 2. Right? I know 50 is 2 times 25, where 25 breaks down to 5 times 5. So okay, I have this root 2 right here, plus root 8, that's root 2, 2, and 2. Got it. Right. And then root 50, that's 2, 5, and 5. All right, break it down into primes. This pair of 2's, this pair of 5's, I can pull each of those out. So I have this root 2, got 2 root 2 here. I got a 5 root 2 here. Aha. Okay. If you like, I could slap a 1 right here and return it. Okay. So I have 1 apple, 2 apples, 5 apples, 5, 6, 7, 8. That's like 8 apples. So apples, root 2. Okay. Here, I'll check this with the calculator, show you guys I'm telling you the truth. Okay. The original expression was root 2 plus root 8 plus root 50. And that came out to 11.31. Wait, what is 8 root 2? It's exactly the same thing. Aha, exactly the same thing. It is working. Oh, yeah. Number 19. Simplify this. Okay, I got 6 square root 3ab multiplied by, got a 4 square root 24ab3. Okay. You know what? Since everything's just straight multiply, I can shove this all under one giant square root. Why not? Okay. 6 and 4 is 24. Pull that out. Got square root. And what else? Um, well, I know 24 is 8 times 3. Here. So 24 is 3 times 8, and 8 is 2, 2, and 2. Okay. So here's what I do. Is I can pull some of these together. And this 3 and this 3 over here from the 24 gives me, 3 squared if you like. Then there's 2 squared and 1 more 2. I got all that from this 24. Now A and A makes A squared, and then B and B to the 3 makes B to the 4, or if you like B squared, you want to think it that way. And so since it's a square root, every pair of something I have I can pull out. There's a 3, there's a 2, there's an A, there's a B, there's another B you pulled out. So I got 24 times 3 times 2 times A times B, and another B is B squared. Okay. And then there's still this 2 left over in square root, so I still got that. Okay. Last thing, I'll just combine these constants. 24 by 6 is 144. So it's 144 AB squared And I do have a root 2 still in the mix. Boom. Darn. 24. Jayla walks 5 blocks north, 8 blocks east to get to the library. So, right. So something about 1, 2, 3, 4, 5 blocks north. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so north, east, the library. Each block is 5 root 10 yards long. If Jayla could walk a straight line to the library instead, how far would the walk be in yards? Oh, so I think I have a good picture, except it's a little small, so I'm going to blow this up to how about twice as big, something like this, like that. Okay. So here's maybe Jayla's house, and here's the library. Okay. And she goes north and then east. But what if instead she just made a straight line shot? Zzz, like as the crow flies, how long would that be? Okay. Let's get some distances here. So they said 5 blocks north, but we're not interested in blocks. We're interested in yards. So each block is 5 root 10. So times 5 root 10. Okay, that's how many yards north she goes. And then it was 8 blocks each, but each block is also 5 root 10 yards. So put it all together, be this many yards altogether. Okay. All right. Well, hey, do you guys see this is going to be Pythagorean theorem? How do you spell that out? Pythagorean theorem, abbreviate theorem. Okay. So you guys know a squared plus b squared equals c squared. As long as you have a right triangle going north and east, and make a diagonal cut, same thing. Okay. So I think this side length right here is the square root of this a being squared plus this b being squared. So let's just do that. Back right there. So it's 5 times the root 10 squared plus 8 times 5 times the root 10 squared. Squared. So let's see. Uh, 5 and 5 is 25. 25 squared. Well, maybe I should just write that as 25 squared because I'm going to take square root anyway, right? Or I think. Let's see what happens. Um, here, I'll just get a number. So 5 by 5 squared. 625 square root 10 squared is 10. So here I was throwing the 0 for the 10. Okay. Plus 8 squared, 5 squared, root 10 squared is 10. 16,000. Okay. Now, yeah, let's just get a numerical example. Maybe with a decimal. I don't know. We'll see what happens. Plus 6250 is this is the square root of 22250. Okay. Now, I wonder if I'm kind of curious if they have a special right triangle. Let me divide a 10 out. Let's see if this does have a perfect root. Okay, now I didn't think it would. Okay. How about 22250 power of 0.5? Okay, I'm gonna wait. Okay. Okay, so this, by the way, is approximately equal to 149.2 yards. Okay. But looking at the answer key, it looks like they applied a factor tree. So 22250. What if I pull a 25 out of that? 22250. I'll just take a shortcut to the end. It breaks down to 25 times 890. It looks like what your book did is to say, well, let's just leave the 890 because I guess you can't really square root anything out of that. And we'll take the 25 out. Square root of that is a 5. So this could be 5 times the square root of 890 of 8 yards. Okay, so here's a good simplified answer. Here's a good decimal approximation if you like. It's about 1.5 football field, somewhere thereabouts. All right, 36. Ooh, we got a fraction with addition. I'm already thinking this is probably going to be some kind of conjugate pair, right? You guys think? Let's find out. 36. All right, so we got 2 root 2 plus 2 root 5 divided by root 5 plus root 2. Right? So let's try conjugate pair. Oh, let's spell it out. Conjugate pair. Right? So multiply this whole thing by What if I do root 5 minus root 2? But I also have to do that upstairs to balance it out. Whoops, this is 5 right here. There you go. Root 5 minus root 2. Let's start. Okay. So that's, we're trying to get all the radicals out of the denominator. It's something that normally math textbooks want you to do. Let's go FOIL first, outside, inside, last. Now, I think we'll also have to FOIL the numerator as well. First, outside, inside, last. I'll just do both in one go here. Boom. So there's the FOIL process done. 2 root 2 root 5. Root 2 root 5 is root 10. Boom, right there. Outside, 2 root 2 root 2 is 2 times 2. Boom. Inside, 2 root 5 is 2 times 5. Boom. And 2 root 2. Okay, that's 2 root 10. Boom, right there. Right there. And then denominator, root 5 is 5. Boom. Outside, root 5 root 2. Boom. Inside, root 2 root 5. Boom. And last, root 2 is 2. Boom. So it's all there. It's all there. Now, interestingly, some stuff cancels out. So that's a fast numerator. This cancels denominator, although that the denominator one was to be expected because that's what the conjugate pair setup was all about. But this greatly simplifies because 2 times 5, that's 10. We're subtracting 4. So that's like 10 minus 4 or 6 if you like. In denominator, we got 5 minus 2. So that's 6 over 3. The answer is 2. The answer is 2. Okay. Yeah, so I did check that while I had the video paused also. The answer is 2. If you go back and you plug in the original expression to the calculator, you'll also get 2. So, same thing. All right. 41. Simplify. We got x plus 1 divided by the root x minus 1. Okay. Oh, I think this is a similar situation. Another conjugate pair type. So I'll do that at thinking times. What if I did root x and then a plus 1? Root x plus 1. Okay. And then let's do FOIL. First, outside, inside, last, and so on. So first, x root x. Well, maybe I'll just write that as x root x. It's different ways to write that. Outside, x times 1, that's x. Inside, root x. Last, 1 times 1 is 1. Okay. Denominator, root x is x. The inside cancels because that was the idea of conjugate pair. I would spell that out. Conjugate pair. And then last, -1 times 1 is -1. Now, okay. Uh, so this should be acceptable. Now, interestingly, I do see there's a root x common to both of these. So what happens if I pull that out? Okay. I do get, do you guys remember factor by grouping? Here, I'm going to group these two together. I'm going to take a root x out of, and I have x plus 1 left over. X plus 1. Okay. Well, over here, I also got an x plus 1. Oh, divided by x minus 1. Okay. So if you wanted to, and say, well, I have like root x worth of apples here. I've got 1 apple over here. And so I could factor the apples out. And I guess root x plus 1, then x plus 1, all divided by x minus 1. Okay. Now, that doesn't really simplify from there, but I mean, that could be simplified. Or, you know what, if you just left it like this, I'm sure that would be an acceptable answer as well. Okay, so there's 2 different ways you could get a valid answer. The right one. 48. Music. Traditionally, musical instruments are tuned so that the note A has a frequency of 440 hertz. Yeah, interesting history to that. There have been different standards over the years, but yeah, modern day musical instruments, 440 hertz represents one of the A notes. Uh, with each higher note on the instrument, the frequency of the pitch is multiplied by a factor of the 12th root of 2. Yeah, what they're talking about here is called equal temperament. I talked about this a little bit in my physics class, right? But that's how you can like change notes or chords or scales, and it all sounds sort of the same, right? Whether you're playing in the key of C or the key of F, you can just kind of slide around. That wasn't always the case. There have been different tuning standards. Like if you go back, say, a few hundred years ago, um, There's like Pythagorean tuning and mean tuning, and there's a bunch of different ones where if you change key, like each key has its own sort of like tone to it. So it's like, oh, if you want to play like a happy song or a sad song, you want to play in keys, the key of whatever, whatever, right? But not so much on modern instruments that have equal temperament. All right, so there's a little history side note. What is the ratio of frequencies of two notes that are six steps apart on the instrument? I think that's called a tritone, wouldn't it? It's a weird sounding. Uh, or tritone. What is the ratio of the frequencies? Two notes, nine steps apart. Express your answer in simple form. Right, so let's do six steps. Like a tritone. Right, so it's I think notorious like the worst interval you can play, but that sounds better. So if I have here, let's just start with 440 hertz, right? 440 hertz. So, which you don't have to. You can really pick any key, but I'm just gonna pick one to uh, have a number on the board. Okay? And then we go six. Let's go six steps above that. So you take your 440 hertz root note, and we're going to do the 12th root of 2. Here, I'll show you guys what that is as a decimal. So you do 2 to the power of 1 over 12. Okay, so 2 to the 1 over 12, by the way, is approximately equal to 1.05946. Okay, so we're about there. So every note has a frequency that's almost 6% higher than the previous note. Okay. Now this would be one step above, but if you want six steps, that would be like doing that six times, or effectively to the power of six, because you're doing right, 12 through 2, 12 through 2, 12 through 2, or you just keep going. Right? Now, whatever root you pick as the root note, or, doesn't matter, it cancels out, because the ratio is just this value right here. And guys, this is the same thing as 2 to the 6 over 12, or 2 to the half, which is the square root of 2, which is your classic 1.414. Okay? So that's the ratio. So if you go up six steps, like six, or wait, did they say six steps? I was doing, maybe I'm doing half steps. Well, okay, or maybe there's a difference in terminology here. I don't know. I'm doing like individual piano notes, including the black notes. There you go up. Okay. What about, they said nine steps. Okay. So that would be, well, if I just cut through and look at the pattern, wouldn't that be 2 to the power of 9 over 12? Or 2 to the power of 3 over 4? Let me see what that is as a decimal. 2 to the power of 3 over 4, same thing. 1.6817, so just round it, maybe about that. Okay. And I'm going to throw in one more. Let's do 12. We're saying steps. I'm thinking like, I'm going to use my own terminology. Okay. Half steps. I think they call it, okay. Or an octave. Okay. Because using the system, what does it mean for to hit a root note and then the octave, right? Now we name that the same note, like, oh, I hit an A note here and an A note here, but it sounds one octave up. It sounds higher. So what does that mean mathematically? Well, it'd be like 2 to the power of 12 over 12. 12 over 12 is 1. That's like 2 times. 2.000 exactly. Yeah. So every time you go up an octave, you're effectively doubling the frequency in hertz. And so number of hertz is a way to quantify that. All right, so that's pretty fun. Racing. Jay likes to race his younger brother while running. To make the race fair, uh, John and Jay start at different locations. Here's where John starts. Here's where Jay starts. But they finish at the same point. Okay, so what I'm thinking is, um, yeah, or Jay is the older brother. He can probably run faster because he has an advantage because maybe he's a couple of years older. Right? His younger brother John effectively gets a head start. You guys see that? Like John is not going to run as far to get to the finish line. Okay, so now it's actually competitive. Okay? The diagram shows, blah, 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 and they got these all marked out in tenths of a mile. Okay? Both of them finished the race in exactly 4 minutes. If they continued at their average paces during the race, exactly how many minutes would it take for them to run a mile? Ooh, right, how many minutes to run a mile? Okay. Radical and express your answer as radical in simplest form. That's exciting. Well, let's figure out how fast they're running, maybe like miles per minute, and then I guess we'll solve the answer in minutes. There you go. Okay. So what's speed in miles per minute? Okay. I think we got to do some Pythagorean here. Here, I'm gonna jot that down. Pythagorean theorem, which says, of course, a squared plus b squared is c squared for a right triangle. Okay. You guys see a nice right triangle here, and also a nice right triangle right here. Okay. So I'll go the distance, the total distance on the straight set. Let's start with John, right, younger brother, friends, is well, it's definitely this 0.2 mile stretch, 0.2 miles. I guess these will all be miles plus this hypotenuse of this small triangle. So that's the square root of a squared plus b squared. So zero point 0.1 squared plus zero point 0.1 squared. Okay. Ah, okay. That's 1 over 100, 1 over 100. It's like 2 over 100. Yeah, here, I'll just do it this way. It's zero point 0.1 squared. Yeah, it's 1 over 50. Hmm. Zero point 0.2 miles plus, and it's square root. So 1 over root 50 miles. Okay. Now, 50 breaks down into 5 times 10, and 10 breaks down to 5 times 2. So but you could pull a 5 out of that. So zero point 0.2, well, zero point 0.2 even. I'll say that later. 1 over 5 if you like, plus 1 over 5 root 2 miles. Okay. Okay, that's the distance that John ran. How about the distance that J ran? Okay, now J runs a little further. Yeah, he also runs this 0.2 mile stretch, so that's the same. So that many mile stretch, right? Plus, right? Um, but this is a little longer. So it's zero point 0.1 squared plus zero point 0.2 squared, and the square root of all that miles. Okay. So what is that? That's like 0.05, which is like 1 over 20. So that's zero point 0.2 miles plus 1 over the root 20 miles. Right? And 20 breaks down to 5 times 4, and 4 is 2 times 2. So you could write this as 0.2 miles plus 1 over 2 root 5. 5 miles. Okay. I think we are good. Okay, so now that's the distances they're running. Right, we want, um, what's the question here? How many minutes? Okay, okay, oh, yeah, okay, so I'm trying to figure out how fast they're running. They each ran this in 4 minutes, right? Right, so I'll say the speed. Well, here, speed is distance compared to time, right? Like miles per hour, meters per second, in this case, miles per minute. Okay? So the speed of John would be, now he did in 4 minutes, he went this far. And already it's also a fraction, it's 1 over 5, that's what point 0.2 is, plus 1 over 5 root 2. And this would be miles. Okay. The speed that Jay was running was, he did also his version of the race in 4 minutes, but remember, he ran a little further. So 1 over 5 plus 1 over 2 root 5. All right, this many miles. Something like that. All right. Minutes. Oh, wait, did I just, I did silly. Why did I do, this is 1 over the speed. Okay, well, here, I'll just reverse that. Oops, sorry about that. I'm supposed to do miles per minute. I did minutes per mile. So if I just swap that, that'd be miles per minute, wouldn't it? Okay. And we're trying to figure out how long would it take them to each run a mile. Okay, so keep in mind, I'm gonna give you guys the upside down versions of these. Okay, so I can say distance equals speed times time. Right? Or if you like, time is distance divided by speed. Right? Like for example, here, if you look at the side of the road, you see a billboard that says The next town is 120 miles. 120 miles. And you're going 60 miles per hour. You think it's going to take you 2 hours to get there? Those 2 hours to get to your destination? All right, that's just a little side example. Right, that's basically what we're doing. So if you take the distance and divide by the speed, that would give me how much time it takes. So what's the time for John? Time for John. Well, the distance would be 1 mile, and I have to divide that by his speed. Right? You know what? The way I wrote it, I did write 1 over the speed, because the speed should be this many miles divided by this many minutes. So maybe that actually helps me out, right? Okay, miles. Yeah, do that. Okay. So I'm going to go ahead and multiply by 1 over the speed, which I have ready to go. Yeah. So 4 minutes and 1/5 plus 1/5√2. This would be miles. Okay. Okay. Right, I'll have to eventually do the same thing for J, but I think what I have to bring in here is a conjugate pair. Right, you guys remember conjugate pair? Did a few of these. So multiply top and bottom by 1/5 minus 1/5√2. 1/5 minus 1/5√2. Okay. Right, so FOIL first, outside, inside, last. And then this top value I can distribute this for. Right, so let's see what that is. So that's on top, we got 4/5 minus 4/5√2. It's all divided by 1/5. 1/5 is 1/25. Outside, inside cancel, of course. And then last would be, see, okay, it would be minus because there's a minus. Okay, 1/5 and 5 is 25. And then root 2 is 2. It's 1/50. Okay. 125 minus 150, that is 1/25. Okay. Okay. So, okay. But you know what? I also have to clean up this numerator because now this also has a denominator in it. Let's do that. So, uh, 4/5 minus 4/5√2. I'm going to multiply this by 4/5 plus 4/5√2. This is 51. Get here. Okay. And then this is all divided by, okay, show you guys this is true. 1/25, oops, it's like 0.04. So if I do 1/25, that's 1/50, that is 1/50. So it's all divided by 1/50, like that. Like this. Okay. Um, okay. All right, so let's do another foil here. So I got first, outside, inside, last. Okay. And so 4/4 is 16/25. Now the inside outside cancel because it's set up to conjugate pair. Okay. And then last is, see, I'm doing this right? Check this out. 25. We're doing that. Right. There. Tell you what, 4/5 plus 5/2, 4/5 plus 4/2. Okay. I still have to, no. Hold on. I have to be careful about that. Right. So I have to get a common denominator. That's what I have to do. Sorry. Let me backtrack a little bit. This is not the correct way to do that. Right. Correct way, we have to go back, is to do 4/5, multiply this top and bottom by √2. That's what I should have done. Okay. Kind of rushing myself here. All right, and then minus 4/5√2. Now the denominator is still 1/50 is what that comes out to. Okay, so still got that. All right, so if you divide by 1/50, that's the same thing as multiplying by 50. Okay, so 50 times, okay. Then all this stuff right here. Now I do have a common denominator, which is 5/2. And then top, I got 4√2 minus 4, or if you like, 4 times √2 minus 1, it's the same thing to go like that, right? Now, okay, now here's what I do. You multiply top and bottom by √2, so I can get rid of this √2 down here, just make that 2. Okay. Now, to I could keep going on. Right? This is clearly going to take a few minutes to finish this puzzle, and this video is going on a little long. But I think you guys see the principles of how to solve this, and the rest is just cleanup. So I'm going to take a sneak peek over here, the addition, and jump to the answers. Right. So, um, right. So the time for John ends up being 40 minus 20 root 2 minutes. Right? If you want to challenge yourself and take that all the way to the end, you can do that. And the time for J ends up being 40 root 5 minus 80 minutes. Right? I'll get decimal approximation because they did ask for simplified radicals. That's why I was doing all that crazy math, supposed to get it eventually to these form. But maybe more practically, say, well, what kind of is that in human terms? This is approximately 11.7 minutes. This one is 40 root 5 minus 80, approximately 9.4 minutes. Right. Yeah, and that does make sense from the start. Remember how Jay was the older brother, hence he's running faster, hence he gave himself, well, the opposite of head start, right? It starts kind of, he has to run before the race, right? Yeah, and that checks out here too. If they both ran, in this case, a mile, Jay is running it faster. All right. All right, so I think that's a good wrap on that. Any question thrown at you, you could answer with that. All right, so got a wrap on 6-5.